All right, let's dive into one of the wildest ideas in all of science, the fact that a black hole can literally slow down time. And to really get how that works, we're going to have to go way beyond the usual explanations and, well, look at gravity in a completely new way.
If you've ever seen the movie Interstellar, this number will probably send a shiver down your spine. It's the absolutely staggering amount of time that passed for one of the astronauts, Romilly, while his crewmates spent just a few hours on a planet near a black hole. I mean, think about that. He aged decades. They barely aged at all.
So how is that even possible? I mean, seriously, how can a few hours for one person be over 23 years for someone else? It sounds like total science fiction, but I promise you it is grounded in very real physics. So let's break down what's actually happening here.
Okay, so you've probably heard this explanation a million times. It's the standard go-to answer. And look, while it's technically true, it doesn't really explain anything, does it? It just kind of sits there.
Yeah, saying gravity slows down time is a lot like saying, well, an apple is red because it's red. It's just restating the problem. It doesn't give you that gut feeling, that intuition for why. But today, we're going to build that intuition. And we're going to do it using a beautiful thought experiment that comes straight from Albert Einstein himself.
All right, the first step here is a big one, and I mean a really big one. We have to completely rethink what we think gravity is. So for a minute, let's just take everything we learned from Isaac Newton, put it on a shelf, and look at Einstein's totally radical new perspective.
So Newton saw gravity as this mysterious force, right? Something pulling you down. But Einstein's model, it flips that completely on its head. In his view, there is no pull. Instead, the ground, right now, beneath your feet, is constantly accelerating upwards, pushing into you.
Okay, think about this. You're on a bus and it suddenly slams on the accelerator. What happens? You feel that jolt, right? Pushing you back into your seat. That feeling is just your body's inertia resisting that change in motion. Well, Einstein realized that what we call weight is the exact same thing. It's just the feeling of your body's inertia pushing back against the constant upward acceleration of the ground.
And I know what you're thinking. This is the immediate, totally logical question. If the ground here is accelerating up, and the ground on the other side of the world is also accelerating up, well, shouldn't the Earth be expanding, like flying apart? And that is a fantastic question. And of course, Einstein had an absolutely ingenious way to solve it.
So, to solve this whole expanding Earth puzzle, Einstein takes us on a little trip. He asks us to imagine a scenario way out in deep space, far, far away from any real gravity.
So just picture a massive ring, kind of like a giant space station, just spinning out there in the total blackness of space. And people can actually live on the inside surface of this thing.
Now, to get what's happening here, we need just one key piece of physics. It's called centripetal acceleration. And all that means is that when you're moving in a circle, even at a constant speed, you're always accelerating. Why? Because your direction is constantly changing, and that acceleration is always pointed towards the center of the circle.
And right here, this is the brilliant solution to our expanding Earth problem. For anyone standing on that ring, the floor is constantly accelerating up towards the center. But because the ring is a solid object, it can accelerate forever without ever actually getting any smaller. This creates a constant feeling of gravity pushing them down into the floor. Puzzle solved.
Okay, so let's just take a breath. We've established that what we feel as gravity is really just the same as being in an accelerating frame of reference. Now we get to the second truly mind-blowing part of all this, the effect that acceleration has on time itself.
And to really get this, we need to look at our spinning space station from two different points of view. First, let's imagine we're just floating in space outside, watching it spin. And then we'll jump inside and see things from the perspective of the people who live there.
So, from our spot floating out in space, it's super obvious that people inside that ring are moving at very different speeds, right? Somebody standing near the center, the hub, is barely moving at all. But someone on the outer edge? Whoa, they are whipping around at an incredibly high speed.
Okay, now we need to pull in another key idea from Einstein, this time from his special relativity. It's called time dilation. And the bottom line is this: the faster you move through space, the slower you move through time. A moving clock always ticks slower than a clock that's standing still.
So for us, the observers floating outside, the answer is dead simple. The person on the edge is moving really, really fast, so their clock must be ticking slower than the clock of the person near the center. Easy peasy. No mystery here at all. It's just straightforward special relativity. But And this is the big but. What about the people inside the station? From their point of view, things look completely different. And this, my friends, is where it gets really, really interesting.
See, from their perspective, nobody's moving. They're all just standing still in their home. They can walk from the center to the edge, and from their point of view, they're not moving relative to the floor. And yet, it is an absolute, objective fact that the person on the edge is aging more slowly. So now they have a paradox on their hands. Why are our clocks ticking at different rates if nobody is moving? Well, they can only blame one thing. What's the only difference between the center and the edge? It's the strength of that gravity they feel. At the center, there's basically no gravity. But at the edge, that artificial gravity is super strong. So they have no choice but to conclude that it's the strength of this acceleration, this thing they call gravity, that's making their clocks run at different speeds.
And this brings us all the way back to Interstellar. It brings us back to our original question. We can now use this spinning spaceship model to finally, truly understand what is happening near a black hole. This comparison here is just perfect. Being far away from a black hole where gravity is pretty weak, that's exactly like being at the calm center of our spinning spaceship. Time clicks along normally. But getting super close to a black hole where gravity is just crushing, that's like being on the outer edge of that spaceship where the acceleration is absolutely extreme. And just like on the spaceship, that severe acceleration leads to severe time dilation.
So here it is, the key takeaway. When Cooper was standing on that planet in Interstellar, the intense gravity he felt was the physical equivalent of standing on the edge of a spaceship the size of a solar system, spinning so fast that he was moving close to the speed of light. And Romilly, orbiting way farther out, he was like someone near the center of that ship. That is why Cooper's clock barely moved, while Romilly's just kept ticking away for 23 long years.
So you see, just saying gravity slows down time, it's not the real story. The real story is that gravity is just what acceleration feels like. And the deeper truth this reveals is that your journey through space is fundamentally tied to your journey through time, which leaves us with a final really profound thought. If acceleration can literally change the flow of time itself, what does that truly mean about the fundamental fabric of our reality?